What's going on, everyone? Welcome back. Patrick here, and moving on to another example dealing with differentiability. We have to show that this function f of x, this piecewise function, is not differentiable at an x value of 2. So just want to give a heads up that this is a pretty complex example. It doesn't look complex right now. This looks like a pretty simple piecewise function, but showing that it's not differentiable, there's going to be a lot of parts to this. So just want to give a heads up that you may have to watch this video a couple of times. I'm going to do my best to explain it, so hopefully you can get the explanation the first time, but my explanation may not be perfect, so you may have to watch it more than once for it to really sink in. But I'm going to do my best. So we got this piecewise function here. First thing I'm going to do is I'm going to graph it. So it's not too complex, luckily. So notice that this function is defined by x squared when all the x values are less than 2. So I'm actually just going to draw a parabola x squared for now, which just looks like that. And then at an x value of 2, what's the y value going to be for x squared? The y value is going to be 4, like that. But notice that it's this parabola for all x values less than 2. So any x values greater than 2, this part here we can erase. And notice that at an x value of 2, it's not defined there, right? The x value of 2 is defined here for this function, which is just a line, y equals x. And so here, that's going to be a hole there, because it's x is less than 2. If it was x is less than or equal to 2, then that would be a solid dot. But it's a hole because it's not defined at that x value 2. Now, y equals x, that's just the line. And notice at an x value of 2, y equals x is going to have what y value? It's going to have a y value of 2 as well, right? The coordinate's going to be 2 and 2, versus this coordinate here for this hole is 2 and 4. So 2 and 2 is going to be right there. Okay, so if we drew this line y equals x from the origin, it wouldn't have too steep of a slope. So this is not maybe to scale. The x values are more zoomed in than the y values. But really the most important part of the graph is this part here, near that meeting point of 2. So it's x, this line y equals x when x is greater than or equal to 2. And then at an x value of 2, there's a coordinate 2 and 2. So this coordinate here is 2 and 2. And it's just going to be a line with a slope of 1 going up like that. Okay, so that's how this piecewise function looks. So notice from the graph we can tell already that at an x value of 2, the function is discontinuous. And notice that it's a jump discontinuity. So far we've dealt with other discontinuous functions, an infinite discontinuity where there was a vertical tangent. We dealt with a removable or a point discontinuity where there was a hole. Now we're dealing with a jump discontinuity, right? And showing that this function is not differentiable at this x value of 2, the process is going to be a little bit different than the other discontinuous examples. It's going to be more complex, in my opinion. So we got to show that this function is not differentiable at this x value 2. And to do that, like we did in the previous examples, we basically have to show that that definition of a derivative, this limit here, does not exist. So applying this to what we have, we're going to have the limit as h approaches 0 of f of, notice the a value is 2, so we'll have f of 2 plus h minus f of 2 all over h. And here is the first problem with the next step. Notice that f of 2 is going to be 2, okay, because So let me write that here. F of 2 is 2, right? At an x value of 2, this function here is defined by this piece, this y equals x. So at an x value of 2, the y value is 2 as well. If this was flipped over, if this was less than or equal to 2 and this was greater than 2, then the y value here would be 4. But in this case, it is 2. So we know f of 2 is 2. And then f of 2 plus h, notice that we have to plug in this 2 plus h expression into this function here, into one of these functions. The problem is that we're going to be plugging in this expression, 2 plus h, into either of these functions depending on what that h value is, and more specifically, if we're approaching that h value as 0 from the negative side or if we're approaching it from the positive side. Now, why is that? Because notice that if we approach 0 from the negative side, it's going to be 2 minus a very small number, right? If h is approaching 0 from the negative side, h is going to be a very small negative number. So it's going to be 2 minus a very small negative number. So that means that this is going to be less than 2. And whenever we have x values less than 2 for this function here, it's going to be defined by this function, x squared. Okay, so as h approaches 0 from the negative side, f of 2 plus h is going to equal 2 plus h squared, because we'd be plugging in that 2 plus h for this function here. Versus if we're approaching this h value as 0 from the positive side, right? So values like 0.1, 0.01, 0.001. We're approaching this h value as 0 from the positive side. So that h value is going to be a very small but positive number. So we're going to end up having 2 plus a very small number. Here we had 2 minus a very small number as h was approaching 0 from the negative side. Here we're going to have 2 plus a very small positive number, which means it's going to be greater than 2. Which means that it's going to be defined by this function here, this x, right? And so as h approaches 0 from the positive side, f of 2 plus h, we would plug in this 2 plus h for this function here, which is just going to be 2 plus h. All right, so that's what makes this example more complex than the other ones, in my opinion, because for the other ones, we were able to deal with this at the end when we simplified the limit, and we ended up having an expression at the end, and then we could look separately as h approaches 0 from the negative side or from the positive side. But for this function, because we have two totally separate functions to the left of 2 and to the right of 2, we have to make this, we have to incorporate this difference here before simplifying. We can't look at this after we simplify, because the simplification process is going to be affected by the function that we choose, if that makes sense. And so what we have to do is we have to kind of split up right here into two separate cases. So we'll have the limit as h approaches 0 from the negative side. And remember, if we approach an h value 0 from the negative side, this f of 2 plus h is going into this function. So it's going to be 2 plus h squared minus f of 2. F of 2, we know it's always going to be 2. And that's going to be all over h. And then here we're going to have the limit as h approaches 0 from the positive side. And remember, as we approach 0 from the positive side, this f of 2 plus h we're plugging in for this function. So we're going to have 2 plus h minus f of 2, which is just 2. And that's going to be all over h. So we end up having these two limits here. So we got to find out what's this limit going to be, and then what's this limit going to be, and then come back to seeing what happens with this overall limit, that definition of a derivative. Now, I quickly actually want to bring back the example from the previous video, the removable discontinuity, the second example in that video, where we had that 2 and 5 point, and then we had that line that had a hole at 2 and 4, and that line was x plus 2. So I'm assuming you watched that video because it was before this video on the site. The reason why we didn't have to split up the limit for that example, even though it was a piecewise function like this, was because notice that to the left and to the right of 2, it was that function x plus 2. So we didn't have to worry about having those two cases. Just wanted to mention that. Versus here, notice that to the left of 2, I've mentioned this already, it's this function x squared. To the right of 2, it's this function x. Right? So I may be repeating myself a bunch of times, but I really want you to understand the difference between this piecewise function and then the piecewise function that we did in the previous video. To the right and to the left of that x value of 2, it was the same function, x plus 2. So we didn't have to worry about this 2 plus h from both sides was going into this function. Versus this one, it's going into 2 separate functions. Right? So anyway, so now what we got to do is we got to simplify both of these here. So starting with this one, we're going to have the limit as h approaches 0 from the negative side. Now 2 plus h squared, you would have to FOIL that out, and that would end up being 4 plus 4h plus h squared after you simplify, and then we're going to have a minus 2. Then this 4 and minus 2, that was simplified to 2. So what you'll end up having in the numerator would be h squared plus 4h plus 2. And this is going to be all over h. Now, unfortunately, we can't simplify this any further. Notice we can't factor out an h that's going to cancel out with this h at the bottom. So we're going to have to do a little bit of work to find out what this limit is. So I'm going to come back to that. Let's simplify this limit as much as we can. And this one simplifies really nicely because notice we'll have 2 plus h minus 2. Notice the 2's will cancel out. And so we would end up just having h over h, which is just equal to 1. Right? H over h simplifies to 1. And then any limit for a constant, the limit as h approaches 0 from the positive side, this could be anything, any variable approaching a number for a constant, it's always just going to equal that constant. Right? So this limit here simplifies to 1 versus this one, unfortunately, we're going to have to do some other work. And what you're going to have to do is, I'm going to show you graphically how you can do this. But if you don't know how to graph this just right away, this graph here is going to take a lot more work because if you remember from rational functions and advanced functions, notice this is going to have an oblique asymptote because the degree up here is greater than this degree in the denominator by 1. Right? So if you don't want to go through that whole process, just make a table of values. So just approach this 0. We're approaching it from the negative side, so you try values like negative 0.1, negative 0.01, negative 0.001. Just approaching that h value 0 from the negative side. If you plug in all of these into this whole function, what you're going to realize is that it's going towards negative infinity. Okay, and the way that this function does look like, if you're interested to see, if you were to take this and plot it on Desmos, there would be a vertical asymptote at 0. There would be an oblique asymptote. It'd be like a line like this. And it's going to look something like that. That's how this function is going to look. Vertical asymptote at 0, and then there's going to be an oblique asymptote, which you would get by dividing this function by that function, doing the long division, and then you'd get that equation of this line, the oblique asymptote. Again, you don't have to do all of this. I'm just showing you visually why, as we approach 0 from the negative side, it's going towards negative infinity. If we were approaching 0 from the positive side, we'd be going towards positive infinity. But we're approaching 0 from the negative side, so it's going towards negative infinity. So I thought I would show graphically why that's happening. And again, not too important. You could just make a table of values for that. And then from here, we can see that this left-sided limit of this overall limit is going towards negative infinity as we approach 0 from the negative side. And as we approach 0 from the positive side, this right-sided limit is going towards 1. And so notice that from both sides, we're approaching different values, which means that this overall limit here does not exist. Remember, this limit here is the definition of the derivative, right, for this function at that a value of 2, at that specific x value we're looking at. So because this limit here doesn't exist, we showed it with these two one-sided limits, it means that this function here is not differentiable at that x value of 2. So whenever there's this jump discontinuity with separate functions to the left and right of that x value you're looking at, this is how you're going to do it. You got to show these two limits here. So yeah, that's how you prove it algebraically. Now, to finish off the video, like I did in the previous example, I actually want to explain to you why we're getting these values, right? Just to deepen your understanding of what is going on. It's not too critical to know, but I feel like just knowing what is happening, it makes you further understand the question, and it's going to allow you to do questions in the future in a much quicker fashion. You're actually going to see how everything comes together. So let's start with this 1 here. Why is this 1 happening? Now remember, the difference quotient, what is the difference quotient doing? It's finding the slope of a line between 2 points that are really, really close to each other. And the point that we're looking at, we're trying to find the slope of the tangent at this x value of 2. So we know that we have 2 and 2 here, this point, that's the y value of this point. And then we're going to have another point that's really close to this point, but it's going to be from the right side. Remember, when h is going towards 0, but from the positive side, we're going to have a very small positive number here for h. So that f of 2 plus h, this value here, even though it's very close to 2, it's going to be to the right of 2. And so we're going to be finding here, what we're doing is we're finding the slope between 2 points, between this point that we're looking at and another point that's getting closer and closer and closer to this point. And notice that no matter how close we get, this slope is always going to be the same. It's just going to be the slope of this line here, y is equal to x, whenever we're looking at this point and any other point that's getting closer and closer. No matter how close we get from the right side of 2, that's going to just always end up being that slope of 1, which is going to be the slope of this line. Hence, why we got 1 over here. Right? The slope between 2 points, between this point, 2 and 2, and another point that's really close to the right of 2, because this h is positive, slope is just 1. And then over here, this negative infinity, we're still going to be working with this point here, 2 and 2, which is where we got that y value from. But now the other point that we're going to be working with is going to be to the left of 2. Something very close, but to the left of 2, because we're approaching this h value 0, but from the negative side. So this is going to be a very small negative number. So that f of 2 plus h, that 2 plus h here is going to be 2 minus a small number. So it's going to be x values to the left of this 2. And if it's x values to the left of the 2, we got to use this function, this x squared. So what's going to happen is we're going to be finding the slope of 2 points with this difference quotient from here to here, from there to there, and we're getting closer and closer and closer to this x value of 2. But because we're not right on that x value 2, we're always going to be closer and closer to it, but from the left side, that other point is always going to be on this function. So we're always going to be finding the slope of 2 points of this point and a point that's on this function, and getting closer and closer. So notice it's always going to be a negative slope, but as we get closer and closer, it's going to become more and more negative, right? So negative, and then it becomes more steep. So let's say this slope here is like, let's say -8, then this slope here is going to be like, let's say -12, then this slope here might be like -20, and it keeps going as we get closer and closer to that x value 2. As this other point goes closer and closer to that x value 2, that slope is going to continue becoming more and more negative, hence why it's going towards negative infinity, right? So that's the intuition of where we're getting these 2 values. Again, not as important, but yeah, I just feel like it'll deepen your understanding of what is actually going on. But nevertheless, we got these 2 one-sided limits, different values, which means this overall limit does not exist. So we prove that this function here is not differentiable at that x value of